I was gonna
Content. So, exam done in class. Alright, which one of these is the one you're talking about? Is it
it's actually all
exam one solved or is it exam one unsolved?
on
So
the
let's do this one and then check answers with that one. And then this is the one we did in class yesterday.
down in class. Look at the solved one because the unsolved, these two are going to be different. It's just that that one you're going to have to go to like collab with somebody or go to art to get answers.
Alright,
Because
let's
it's what it
see.
usually
One
does.
is xy prime plus y equals. Right. So what's
Okay, I think we can begin. So, as I said, the exam tomorrow will cover only from chapter 1 to chapter 3. So, for chapter 1, there are not so much to talk about because it's just like a video to know what is differential equation and the order of that. And I know you're pretty good at that. So, we just start from chapter 2 because it covers a lot of materials. So, the first, like, so chapter 2 has, I separate that. So one is, I think that, yeah, for chapter 2.2 is separable equations, and 2.3 is linear, and then is exact. So basically, chapter 2 tells you like different types of differential equations, and you need to think which method you need to use to solve like this kind of differential equations. So for the separable, the separable is the easiest. So whenever you get an equation, you need to once you solve the equation, you need to ask yourself, oh, is this separable? Because separable is the easiest. You always want to solve the problem with the easiest way. So for separable, you can separate gx and hy. So you put all the y on the other side and all the x on the right side, and you take integral on both sides. So that is for separable. So I think this one's easy. And for linear, so linear equation, you need to, so first the equation should meet this formula. So you only have, so you have a1x, a0x, and gx here. And remember, there's no like a y to something. If there's another function like yx, then this is not linear. So for linear, on the right side of the equation, you only have a function of gx. And to solve that, you want to make the parameter in front of dy dx always be 1, because you need to find your, so, and for this one, you need first divide both sides by a1x, so you can get dy dx plus a0x, a1x y, which equals to gx over a1x. And then, so this whole function is your px, and this whole thing is your fx. Then you need to find your integrate factor, which is e to the integral of your px, and you multiply your integral factor with your y prime equals your fx times the integral factor, and it takes the integral on both sides. So that's for the linear equation. And for the exact, the equation will look like this. So you have dx and dy, which are separate, and you have a function of both x and y in front of dx, and both function of both x and y in front of dy. But sometimes this one is looks similar to a homogeneous. So you want to. So the first thing, if the question is not say that, oh, this is an exact, you need to verify that by yourself. So to determine whether the differential equation is an exact, you need to make, so remember, the mxy is always in front of dx, and nxy is always in front of dy. So sometimes you just change the position, but you need to know which one is mxy and which one is nxy. So to determine whether this one is exact, you need to take dm x over dy and dxy over dx. So if these two are equal, then this one is an exact. And to solve an exact, we take integral. You can take either mxy or nxy, and you take integral of that, and you get so that it this integral of, let's say, mx dx, and you get the equation of x, but you also don't forget there is a function of hy, and after you get these things and you take the derivative, so this part is equal to the nxy, and you figure out what is your hy, and you put it back to here and set the whole function, whole equation equal to c. So we will go to examples. That is so basic things for these three types of equations, and after that, I think that's so the PowerPoint is on the I emailed you, so you can always look at it. So yeah, and the others. So the next thing is the substitution. It's a big part of chapter 2. So for substitution, there are three types of differential equations. So the first is homogeneous equations. So as I said, there's a little bit like confused about homogeneous and the exact, because they both have the the function things and have dx, and sometimes the things like dy. So you need to know whether the differential equation is exact or it's homogeneous. So and always the homogeneous. So to solve the homogeneous equation, you need to set your u equal to what? Sorry, it's y equal to ux, or sometimes you can set x equal to uy, and you find your dy dx, which equals to u dx plus x du, and you replace dy dx and y from the original equation and make it into separable. So the modified equation will only contains u and x. So and after that, when you get a function like a function, I don't know, like something. And we'll go to examples and I will talk about that. I mean, at last you need to replace u back to y, because you want to find the function of y but not u. So and for the Bernoulli equations, you always have. So the order of y is always greater or equals to 2, because if your n is 1, then you can combine pxy and fxy, so it will become linear. And if your n is 0, then this part is just fx, so you don't have this part. I mean, you don't have y here, and it's also linear, so it's not a Bernoulli. You can use linear method to solve it. It's much easier than use the method to solve Bernoulli. So once the n is greater than 2, and you know that is a Bernoulli, you set your u equals to y to the order of 1 minus n. So n is the highest order of y. But you always need to find the highest n. And once you replace your then y is simply equal to u to the 1 over 1 minus n. And then you need to find your dy dx, which is equal to, you just take the derivative of this part, and you have, so 1 over 1 minus n times u, and that is this things minus 1 du. And just as the homogeneous, you replace y and dy dx with these two things. And after you modify the equation, then you should get a linear one. So the last thing for substitution is ABC. So for ABC, it's a little bit special, because here you have a function of both an x and y. So what you need to do is you need to set this whole things equals to u, and you take the derivative of that and to find what is your dy dx, and again replace y and dy dx with u and x, and then finally you can make the equation into a separable one. So that is some basic idea about substitution. So for chapter 2, what you need to remember is that substitute. Sorry, you have a question?
Yeah, or maybe correction.
Oh,
So
yeah.
you said n has to be greater than or equal to 2,
Yeah.
but isn't it more the case? Like it could be -1. It just can't be 0 or 1, right?
You mean negative?
Like n can be anything that isn't 0 or 1. It doesn't necessarily have to be greater than 2.
Like n equals
Like
-2.
Like n greater than or equal to 2 excludes n equals negative anything, but n could be negative something, because then it'd be 1 over y to
Yeah.
something.
Yeah, I think you're right. 'Cause I didn't notice that. But I will check that. So is that from the book? Says that? Or
Well, it's just what he said in class, and
oh, he said that
it
in
works
class.
with
Oh, then.
yeah.
We've
And
solved
also,
problems
but,
like
but
that.
don't let n equal to 0 and 1. So yeah. Sorry about that. I didn't notice. So yeah, that's almost for chapter 2, and so let's. Do you have any question about the practice exam? So we can go over some problems about it. Because there are 2 without, so one with solutions, but other has not solutions. So. So you already looked at the practice exam, right? So for this one, I think I can put it here. So, okay, for this one, the first one. So when we take a look at this, so we know that we can, when we put the 7y on the right side, so it will become dy dx equal to 7y. And we know that this one is separable because we can separate x and y, so it will become this, right? And we'll take integral on both sides and plus the constant. We know that, so at here is 1 over 7 ln y, which equals to x plus c. So ln y is equal to 7x plus 7c, so that is c1. And you take the exponential, so you can get y equals to here c2 e to the 7 e to the 7x. And notice that this problem is giving an initial condition, so you need to, when our x equal to 0, so that is c2 times e to the 0, which equals to 2. So you can figure out that your constant here is 2, and you put your constant back to the equations, and then finally you get yx equals to 2e to the 7x here. So the first one is separable. And so for the second one, so which would you think, what kind of differential equation of the second one? Yep, so
Yeah.
linear, right? So because at the right of the equation, you only have a function of x, you don't have like any function of y. So this one's linear, but since here, so y prime is equal to dy dx, So if we want to find our integral factor, yeah.
Are we gonna go through this whole test?
I mean,
Or are you just doing a few problems just to show?
yeah, I want to do like a few of them, but if you want me to go over all of them, or
No, I was just gonna say, because if we were gonna go through all of them, could like we try doing them and then you solve them?
yeah.
You know what I mean?
No. What do you mean?
Just like, because if you're gonna do all the problems, then it's like let us try to solve it first before you do it,
Like, take
so
it.
that we could practice. You know what I
Take
mean?
it like
Yeah.
the test.
Yeah,
and then
exactly.
self-grade.
So then.
I mean, we can do that later. I just thought you were just gonna do all the problems right now. That's what I was
No,
saying.
I just want to. But if you don't, I can leave this problem for you, and I will find some examples on the book. So
No, it's fine. You can just keep going. If
Yeah.
you were just gonna do a few problems, it's alright.
Yeah, so I just want to but
Mhm.
I think almost. Yeah.
You know what I mean? That's what I wanted to do. That's what I thought we were
Yeah.
coming here for. Like,
Okay, I
at
know
the
what to
end.
do. I have another practice exam that you don't have, so let's do that one. So do you have this one? Is this one he posted on Blackboard or
Yeah,
not?
dude, that's what I used to do.
Yeah, I think so. I don't think he has this one on Blackboard. So this practice exam is from last semester. So,
Okay. Just put it in my hand.
but it has some answers on here. So, but we can take a look at it. So first one. So first one is separable because you can separate both x and y. So to do that is
Oh, I know, yeah. Yeah, exactly.
so you can put here y prime is dy dx. So if you put your y, the one multiply y on both sides, so you can get y dy equals x 1 plus x squared dx. And then you take integral on both sides. And then for this one, so almost all the practice example are the same through semester. So for this one, it's just the same as the one we just talked about. But you need to set the parameter in front of y prime equal to 1. So what you need to do is to divide x on both sides. So we get this. And then, so this part is your px, and 8 is your fx. Then you find the integral factor, which equal to this. And you have e to the 3 ln x, which is equal to x squared. And you take integral of both sides to get your y. And and for this one, because at the right you have the order, so the order of y here is 4. It's not 0 and it's not 1. So you need to so we can know that this one is Bernoulli. So and what we need to do is, as I said, you set u equal to y 1 minus 4, and you have y to the negative 3, and your y here is u to the negative 1 over 3. And when you take dy dx, so you just take derivative of u to the negative 1 over 3, you have negative 1 over 3, and the u negative 4 over 3 du. And you replace dy dx with this part and y with this part, and try to solve the equations. And for this one, so for this one, so if you don't look at this, so which method are you gonna use to solve this?
The paper itself is white,
Yeah,
so
I
we
know,
still
but-
see.
Yeah, so for this one, yeah, okay, so it's separable, but the main point he put this on the exam is he wants you to know how to using partial factoring. So I'm gonna talk partial factoring again. So for that one is dp. When you separate this, you put p times phi minus p on the left side and dt on the right side. So here we have 1 over p times phi minus p, and for partial factoring, we assume that this thing is equal to a over p plus b over phi minus p, and so this whole thing is equal to, and here you use a times phi minus p, so that is phi a minus a times p plus here is bp, right? And because these two are equal, so the denominator should be equal. So here on this part, when we combine the p together, and we have phi a plus so b minus a p over p phi minus p. So we want to set this whole thing equals to 1 because the numerator is already equal to each other. But so we set these things equal to 1. Here we notice 1 is a constant, and for this part, the only constant here is 5a, and we do not have any p at the right. So what we need to do is we write down we set 5a equal to 1, and the parameter in front of p is equal to 0 because we don't have any p here. And in this case, you have two equations, so you can solve for a and b. So a is 1 over 5, and b is 1 over 5, right? So after you figure out a and b, you put it back to your equations, and here, so you replace a with 1 over 5, and here you replace b with 1 over 5, and you put it back to your differential equation. Yes, here. So you have, so here is you have 1 over 5 p plus 1 over 5 phi minus p dp. So right now we know how to solve this one, right? And when you put over, like drive the 1 over 5 out, and you take the integral of that, it simply become log p, and here is negative log phi minus p. So that is the basic idea of partial factoring. So do you have any question about partial factoring? Or okay. And so then it goes to the chapter 3. So chapter 3 is so for chapter 3.1 is all about the linear models. So I have talked about this many times, but I will go over this again. So there are 4 basic linear models in 3.1. So I consider growth and decay as the same thing because they are sharing the same equations. So for this, it's like a population growth, and but sometimes it asks you like a special decay or ratio decay, and he might like change PT to AT or some other, but you should know that it's just the same thing. So for the growth and decay, the linear model you need to use is PT equals P0 times e to the KT. So K is a P0 and K is a constant. So for P0, usually the initial, like the initial population and if the question is not giving you the initial condition, you need to find the information from the sentence. Like it may say, oh, after like 5 years, the population will become like 2,000 or 3,000, something like that, and you put that back to the equation and solve for your constant. So, and the next thing is the cooling and warming thing, and you need to remember so these equations. So here you have three conditions, three constants. So the first is Tm. So Tm is the environment temperature, and which is constant. So and the Cnt is also constant. That's so you need to, sometimes it will like just directly tell you what is your Tm, like when you put a metal in the boiling water and the boiling water, which its temperature is 100 Celsius, is your Tm, because the temperature doesn't change and it's the environment temperature around your material, like the metal, and because if we know this one and we still have two unknown constants, then the question will give you two conditions. So like one is after 2 minutes the temperature increased by 2 degree, and after 5 minutes it will increase by 8 degree or something, and you put it back to solve for your two constants. So and the solution here, it only has one tank, and you need to know, so A is amount of salt in your tank. So and it's dA dt is equal to the salt come in minus the salt goes out. And once you get the differential equations, so that one will become a linear one, and you try to solve that. And the last is the RL circuit and the RC circuit. So for RL circuit, you only has a resistor and an inductor. So the basic idea of this circuit is that the total voltage of the circuit is equal to the voltage across the resistor and the voltage across the conductor. So we know that the voltage across the resistor based on Ohm's law is just the R times I. And the voltage across the inductor is L times di dt. So this is usually constant, and you write down your equations as the voltage across the resistor plus the voltage across the conductor. And this thing is linear because it's a constant, and you try to solve it. And for the RL circuit, you will get a function of IT. So, but for the RC circuit here, and so instead of inductor, we change this one into a capacitor, right? And and here we know that the voltage across the capacitor is equal to 1 over. Yes, is Q over C, and the voltage across the resistor is still R times I, but we know that I is equal to dQ over dt. So instead of put I here, we put dQ over dt here, and also, and finally we know that dt is the voltage across the resistor, which is R times dQ dt, plus the voltage across the capacitor. So here is Q over C, and finally we got the equation of Qt. Right? So for the RL circuit, you get the function of IT, and for the RC circuit, you get the function of Qt. So that is the 4 models for the 3.1, the linear models. And so you have any questions so far? for the linear models. And you should remember all these equations. And so let's take some examples. So for this one. Okay, so for question 5, okay, let's read. So a potato at 240 degrees is removed from an oven and placed into a room at 70 degrees. So at here, we know that the potato at 240 degrees is moved from the oven, and we can know that the initial condition here. So when T equals to 0, the temperature of the potato is 240 degrees, right? And it placed into a room at 70 degrees. So this 70 degrees is the Tm, because when you put the potato into a room, and the temperature of the room will never change, and it will so that is the environment temperature around the potato, right? So that is your Tm, and so right now you can write down your equations as 70. So here is your Tm plus C e to the kt. And right now our goal is to find the two constants here. And so after 3 minutes, the temperature of the potato is 210 degrees. So we know that when T is equal to 3, so T here will replace with 3, and the temperature is 210 degrees. And it asks you what will the temperature of the potato be in 8 minutes after being removed from the oven. So at this point, we have two unknown constants, but we only drive one equation. So we need to find another equation. But remember here, we have the initial condition. So that is when T equal to 0, temperature is 240. So we can use that one and put it here. So when T equal to 0, that is 70 plus C times e to the 0, which equals to 240. So right now we have two unknown conditions. We have two unknown constants, and we also have two equations. So we can use these two equations to figure out what is C and what is K. So for this thing, it's just 70 plus C is 240, so that should be 170 degrees for C. And then you put C back here and solve your K. Sometimes you don't need to solve for K. I mean, you can just directly solve e to the K and put e to the K, the whole part back to the equation. And once you figure out your C and K, then you set your T equal to 8, which is what the question asked about, and try to figure out the temperature. So that is for the temperature problem. And for 6 is a tank problem. So it's always a good idea to draw a picture of whenever it comes to a tank problem. And I think he really likes tank problem because based on the previous practice exam, he always put tank problems on it. So for the tank problem, so there are 3 conditions related to the tank problems. So the first is R in is equal to R out, then the solution in the tank will remain the same. So, and another is R in is greater than R out. So if R in is greater than R out, we know that the solution will accumulate in the tank. So let's say the initial value of the tank is 300, and And if it's coming with 5 gallons per minute, and it leaves at 3 gallons per minute. And then we know that, so for the first one, the concentration of salt is simply A over 300. So that is the amount of salt, that is the volume of the tank. So the concentration is A over 300. But when R in is greater than R out, so the solution will accumulate, and we know the volume is not 300 anymore. Because so at this point, we know that the rate coming in is 2 gallons per minute greater than the rate goes out. So we have 300, but the solution will, so 2 gallons per minute times T, the volume will add it to the tank. So the concentration for the second solution, for the second condition is A over 300 plus 2T. So, and then for the last one is R in smaller than R out. That means here, if we have 3 gallons per minute in, and but we have 5 out, we know that finally the solution in the tank will goes away. So we lose 5 minus 3 gallons of water per minute. So then we need to minus 5 minus 3, which is 2 times T. So the only thing varies from these 3 conditions is the concentration of salt in the tank, and others are almost the same thing. So, and let's so for this one, so a tank initially contains 3 gallons of saline solution with 4 pounds of salt per gallon of solution. So if we draw a tank, and we know that it contains 300 gallons of solution in it, and it has 4 pounds of salt in it. So a solution has 3 pounds of salt per gallon poured into the tank at a rate of 2 gallons per minute. So the solution goes in with 2 gallons per minute, and it contains 3 pounds of salt per gallon. And it says that the solution leaves the tank at the same rate. So when we read this sentence, we know that the solution leaves the tank at the same rate, which is 2 gallons per minute. So once we draw this picture, then we need to drive our equations. So we know that dA dt is equal to R in minus R out. So here, our R in is 2 gallons per minute of solution times the 3 pounds of per gallon of salt. So that is 2 times 3. So and the rate goes out is at 2 gallons per minute. And so, but we need to time the concentration of the salt in the tank. So as I said, there are totally a amount of salt in the tank. And because the rate come in and the rate goes out is equal, so 300 gallons of solution maintain the same. So we put 300 at here, and then you have equations like this. And because this is a linear one, so you can solve this by finding the integral factor. And here I want to mention that it says that the solution has 4 pounds of salt per gallon of solution. So that means the tank originally had 4 pounds of salt in it. So when our T equal to 0, it already has 4 pounds of salt. So our A0 is simply 4.
Times 300.
No, 4 times.
Oh yeah. So that is our initial condition, and but we still let's see. Use the tank, so find the function A and find the amount of salt in tank. Yeah, so that is how to solve the tank problem. But so here I want to change a little bit. So at here, if I change the rate of solution coming into 4, then what do we need to? We know that the solution will accumulate, so there is not 300 gallons in the tank released anymore. So here we know that the rate coming is 2 gallons per minute greater than the solution goes out. So per every minute there will be 2 times T volume of solution accumulate in the tank. So at here we need to plus 2T. So this is your concentration of salt when the rate of solution coming is greater than R out. Yeah?
How did you get 2? Is that from rate out or you
Yeah.
get rate in?
So here you because here you have 4 gallons per minute, so it goes in, but you don't have 2 goes out. So 4 minus 2 is the 2. Like if there is 5, then it's 3. So just use the subtract those 2 rate. And if I change, so here is U2, but if I change this into 5. So now the rate goes out is greater than the rate comes in. So we know that the volume in the tank will decrease, right? So here, instead of plus 2T, we need to use 300 minus, so 5 minus 2, 3T. So at here is the only thing that varies from the 3 conditions for the tank problem. And okay, so think for the last one of this practice exam is another differential equation. Oh, there are 2 left, I think.
That is not exact.
Yeah, I really don't. Please don't say this part, just okay, so for this one, so we'll first solve this one. What do you think about the differential equation?
That's kind of simple.
Yeah, actually there are many ways to solve this one. So the first is when we multiply dx on both sides and move this part on the left, we can get which equals to dx, right? So I can tell that this one is both, and I don't know whether it's exact, but this one is a homogeneous because the order in front of dy so is 1 and the order in front of dx is 1. So actually it's a homogeneous. So if you want to treat this as a homogeneous equations, you can set y equals to ux and then dy dx equal to u dx plus x du and solve it. But
it's exact as well.
yeah, and but this one is exact as well. Always exact is always easier than a homogeneous one. But if you need to check whether the differential equation is an exact before you solve it, because sometimes if it is look like an exact but it's actually not an exact, you use the method to solve exact and you just get the wrong answers, right? So let's check this first. So yep. So here you need to find what is your mx and what is your my. So as I said, the function in front of dx is always your mx, and the in front of dy is your, sorry, here's my. So, and if we check it, we take dm over dy. Here when you take dm over dy, you treat your x as a constant, and you know that so 1 is 0, minus 0, and the derivative of y is -1. And then you take dn over dx. When you take dn over dx, then you treat your y as a constant. So you have here the derivative of x is 1. Wait, it's not.
It's because they're on the opposite side of the equal sign. They need to be.
Yeah.
So
Yeah, sorry, I made a mistake. So, yeah, you need to put them on the same side. So,
Just subtract from both.
yeah, you need to make this this
They give you plus x plus y minus 1.
plus x plus y minus 1.
Because you're just distributing the negative then.
Sorry about that. You need to put this on the same side. And here this is our mx, this is our my. So here you have the not -1, but you have so it's 0 plus 1 plus 0 is 1. So they are equal, so we know this is an exact. So then to solve an exact, you take the integral of I'm going to write that here. So you take integral of either mx or ny. So here, because I saw that ny is only x plus y, so I choose to take the integral of ny. So it will become, so x is simply a constant. Don't forget to function of x. And then you take this whole thing. So here is your, and you take this whole part because here we take the integral of dy, so at this part we need to take the derivative of dx, and then you can get y plus, so here you don't contain any x, so it's simply 0, and here is g prime x, and this equation should always equal to mx, so that is x plus y minus 1. And to check whether you are doing the correct thing is at this point. So at here you have y on the left side and you have y on the right side, and g prime x is x minus 1. So if at here you still have a function of y, let's say you still have like a 2y squared, then that means you are doing the wrong things maybe in the previous process, because your g prime of x is only a function of x, so you cannot contain any y here. So it's a way to check whether you're doing the correct things. But at here with our g prime is simply becomes x minus 1, because we cancel y on both sides, and when you take integral of that, you can get your gx equal to square minus x, and once you get your function of gx, you put it back here, so the final function is simply become, so this part, that is xy plus 1 over 2y prime, and plus your gx. Your gx here is 1 over 2x squared minus x, and you set this whole thing is equal to c. And here it just modify a little bit, I guess. So that is how to solve an exact. Okay, and so you have any questions so far? Like how to distinguish whether it's an homogeneous or determine whether it's an exact, and how to solve it. Okay. So the last one is So, sorry to tell you what to do. So for this one, so we can first check whether it's an exact. So at here, this is your mx, here is your y, and when you take this to y, but when you take dn over dx, which is negative y. So these are not equal to each other, so we know this one is not an exact, though it looks like exact, but it's not. So if it is not an exact, then we need to consider whether this is a homogeneous, because it also looks like a homogeneous equation, right? So here we can see the order in front of dx is 2, and here, because x is multiplied by y, so the order is also 2. So this one is a homogeneous one. So to solve this one, you set your y equals to ux, and your dy is u dx plus x du. And you put everything back to the equations, so you get, I don't have many space here. So your x squared is u squared, x squared, and plus x squared dx, and minus x times y is ux, and your dy is u dx plus x du. And here we have x squared and x squared, so we pull out the x squared, so you have u squared plus 1 dx, and minus your u x squared, so here x times x is x squared, so u dx plus x du, which equals to 0. And because the first part will have the x squared, the second part will have x squared, so we can divide it by x squared on both sides. So we just get rid of the x squared. So here is still 0, but here you get rid of x squared, and you don't have x squared here. And now we need to combine the dx part together and the du part together. So for the dx part, here you have u squared plus 1, and that here you have u times u, so that is minus u squared dx. And for du, we only have u times x, which equal to 0. And here, so u squared and u squared just simply cancel each other. So we have dx minus ux du equal to 0. So at this point, we can see that the equation can be separable. So, and it only contains x and u. So if you put it look like this, and we put all the x on the other side, so we have dx, so I put x is equal to u du, and we'll take integral on both sides. You have log x equals to u squared plus c, and actually we don't need to do that because we want the function of y. So because our y is ux, so we know that u is equal to y over x, and we want the function of y, so we need to replace our u back to y. So this is become u squared over x squared plus c, and then when you put everything on that side, you have this log x minus c, and u times 2. So y squared is equal to this. What? Yeah. Sorry. Just do. We write it up. Okay. So when we say on the left, I have 1/2 y squared over x squared equal to ln x minus c, and I multiply 2 on both sides. So get rid of 2. 2, and then multiply x squared. So finally we have our y squared equals to this. Right? So here it doesn't matter whether it's a minus or a plus. I mean, you can just put it as plus because c is a constant and it can be any numbers. So that is how to solve the homogeneous one. Yep.
Two questions. One, how did you get the order for dx and dy both as 2? Because for dx the order is 2, but for dy isn't the order 1?
You mean you like how to find the order?
No, the highest order. Yeah, I got that.
This one, right?
Yeah, and dy. How did you get that as 2?
Oh, because here the order of y here is 2, right? And the order of x is 2, but they are so that is plus sign here. So when you have plus, so the order is the highest order of no, it's not highest. I don't know how to say that, but they have the same order of 2, and here is a plus sign, so the order of this whole thing is 2. And for here, the order of x is 1, and the order of y is 1, but they are multiply each other.
Yeah,
so that is 2.
Okay.
So that's why the order of this part are the equal. I mean, if here is not a plus sign, it's a multiply, then the order is simply 2 plus 2 equals 4. But here is a plus sign, so it's just a 2.
Another question. The answer there is showing x squared 2 ln x plus c. Over here it's 2x squared.
Yeah, I have minus c here, right? Is that your question?
No, because the c isn't being multiplied by 2. Only the ln x is. Is he taking a new constant or?
Because here if you expand these things, so here if I have c here and you have 2c, so because c is a constant and can be any number, and the 2c is also a constant, so I can simply say this is c1, right? So that's why, I mean, it doesn't matter if you put like this or this, it's also correct. It's just actually it's a different c, but it's just a constant and can be any numbers of it. Yeah, so that is practice exam from last semester, and but based on all the problems, you can see what probably will be on the exam. So they are not that different, but you need to, like, the first thing is you need to distinguish the differential equation, like the separable, linear, exact, and the substitute. There are 3. So the homogeneous from Julie and the ABC. And for the chapter 3 is basically the 4 models, as I said. So remember the 4 models, and whenever get, so it's obviously to know which model you should use. So for a population or a light intensity or fossil decay, something related to that, you need to use the population growth or decay model. And everything related to temperature, then you need to use the temperature model. And for the tank is obviously, and find the R in and R out and to solve it. And for the RL circuit and RC circuit, you should know that for the RL you are going to find IT. So, but for the RC circuit, you are going to find QT. So that's basically what he will cover in the exam. And yeah, so it won't be difficult, and you have plenty time. So just try your best and like. So do you have any questions? I can yes.
Are you gonna send us this exam?
This one?
Yeah.
I mean, if you want, I can send it, and because I still have like 2 more of the practice. If you want to do it, I can send it to you. Yeah. And so before the exam, if you have any difficulties solving the problem, and if you wanted the answers, and just email me, and I can help you to solve and feel free to ask me. You're welcome, and hopefully this can help you. And we have I need to sign it.
No, because what my friend
Okay. Yeah, I will send that to you.
Yeah, dude, that was ridiculous. It's like a one-page like thing. Like his is like 4 parts, 10 problems. It's fucking ridiculous.
I'm glad I had humor because now this
Yeah.
is great.
This is great.
But I also can modify by.
Because you can't.
Where are we going?
Yeah, so that's conversation
That's so true though. I've never had all the tests.
Because we had no idea what.
Yeah, so this
There's a
is.
lot on the website.
Yeah.
I forgot about that little.
It's just
Different
the.
the pinata, like
That's like the two
the
times
pinata is the size of a flea,
Oh,
and you got like
yeah,
this
so.
this
You mean he?
like
You mean the professor?
straw-sized bat. You're trying to spot at it. You're blindfolded.
Last semester, but.
That's his test.
So,
Yeah, exactly.
I cannot guarantee that.
First off, you can't even tell if
It,
you're
it,
good or not.
it's just
Second
the
off,
same as the 110.
You're lucky you got 3
once
feet
you
on
know
the
the
tip.
110
Like, kick
structure,
your ass.
so if you have 210, it's the same. So this is A and this is
I can't come to dinner at the house because it's at Wednesday and I have friends.
God.
So usually the
Actually,
amount of,
There are?
Yeah.
usually
yeah,
the
I mean,
amount
what
of,
do they have?
the volume
I don't know.
of
You should come.
A can be.
And they have the vegetarian meals
And
too.
Actually, no.
what you
I don't
need
want
to
you
do
to
is
go.
you need to find your DA, DT,
It doesn't start at
which
6
is.
though?
Yeah, it does, but we can be late.
Yeah,
So you can just say like,
And
Just say
you
I'll
find
be in
class,
so
like,
where,
over here.
where the way the sound may come in. So like here you have like from B to A. So if so if you have time, I can show you the example. Yeah. I think I have one.
I was in his class last time and the last semester and he yeah, 3 years. I feel like he does them pretty similar to the practical exams. So when I look at them, I feel pretty good, but I'm always afraid I'm just gonna get in there and something is there and I'm like, oh my god. Also, he said it's gonna be up to 4.1. Is that true though? The practice exams don't show any of that.
Yeah,
And I'm hoping.
So did he say that there will be content available?
Well, he said that originally, that was like a week or 2 ago, but the practice exams haven't had problems from it.
Because I think last class he said only contains chapter 1 to 3.
Okay,
But
I might have not heard that.
yeah, I mean I'm not sure about that. But
Yeah.
So okay, so for this one, it's a major tank problem. So what you need to do is, so if you want to find the ADT, so that is R in minus R out, right? So here R in, you have
4.
well, wait.
Rn would be 4 for DADT because 1 would be coming from B and 3
Yeah,
would be coming
yeah. So here you need to find, so here you have salt coming from B here, and it's 1 gallon a minute. So the rate is 1. So and you need to time the concentration in B, right? So B over I don't know how many this is, like 500. I don't know. Over 500. So that is one part of the salt may come into tank A, and here there's another arrow which towards A, but here you have pure water. So that is so these are all the R in, but you have 0 times 3. So that is all your R in. But if there's not pure water, if it says is 4 pounds of salt per gallon, so you know that here you have another way.
12.
Yeah, so that is your R in, and you need to minus the R out. So if we only look at tank A, we can see that there's 1 arrow. So that is where the salt may leave tank A. So it's at the rate of 4, and when you time the concentration of salt in tank A, so which is 4A amount of salt over 500. So that is the equation for DADT, and the same thing for dB dt. So I said that is equal to 4. So the rate of salt coming in is from this way. So that is 4 times the concentration of salt, which is 8/500. So actually these two parts are exactly the same because amount of salt leaving tank A will go to tank B, right? So that is the only way salt may goes into tank B. And if we look at the rate goes out, we'll
It's
see.
the exact same, only the opposite.
Yeah, this one is exactly the same for this part. So that is 1 times B. But notice here we have another error. So that is a mixture, and it's at the rate of $3 per minute. So we know that. So the rate times the concentration is B/500. So this will also leave the tank. So that is the whole equation you drive. It's actually the same as the single tank problem, right? You need to find your R in and R out just by simply looking at the arrow, if arrow towards that, and then you should see whether they contain salt. I mean, for that one, it's pure water, so no salt coming. But here, it contains some salt, so you need to put that into RE, and so. But I mean.
Yeah, the second one can be simplified pretty easily if you
Yeah,
add
it's
amount
happy
take
because
the
there are the
formula
same thing. It's just
A minus
4, right?
A minus B over 4 times A minus B over 5.
Yeah, so it's only 205 minus, so that
2
is
over 2B
2b
over
over 205. So actually it's pretty easy, and it won't ask you to solve this system differential equation. Once
Oh,
you
thank God.
once you try this equation out, then just
Then I'd be
simplify.
really nervous.
Yeah. So that's probably it. I think that's it. Thank you. You're welcome, and good luck for tomorrow.
Could you send out the other practices?
Yeah, can I have your email address right now so I can send it to you? I think I have all the practice example here, so I just forward it to you. Can you type your email address? Oh, wait, let me stop recording this.